Hey everyone, my name is Ben Smith. Hope you've been enjoying the talk so far. I know I have. For my talk, I'm going to be talking about raw WASM, handcrafted WebAssembly demos. And what I'm really excited to tell you about is what these are and how I make them. And so let's just get started, jump in. So what is a raw WASM demo? Well, over the past 3 years, I've been making demos much like this one. This is the first one that I ever made. It's called Doomfire. It's a very popular effect, popularized by the game Doom. After that, I made this Metaball effect. It's a very popular effect too, some sort of old school. One of the things that I like to do with my raw WASM demos was to make them as small as possible. So you can see here that I tried to make it 452 bytes. This is one of the most important parts of raw WASM is getting these demos to be nice and small. The next one I made was a nice little ray tracing demo. So you can see here some balls flying around, some shadows, and some reflections, all in 1400 bytes. After that, I made a little snake game, a little bit different than the one that you might have played on your Nokia. This one, you actually rotate the snake in circle and try and collect the apples. After that, I made probably my most popular one, which is a little maze race demo, complete with a random maze generation. And after that, I made a Chip 8 emulator. If you've never heard of these before, Chip 8 is a sort of almost like a fantasy console that allows you to play very low resolution games. This one in only 1,000 bytes. Most recently, I made a little Dino game, very much like the Dino game you might have played in Chrome. 2020 bytes. I actually tried to make this exactly as many bytes as the year that it came out. And then finally, I've done one you can see here, which is a little inflate demo using the same decompression routine as Zip. So you can see here that I just unzipped Alice in Wonderland, and it was 152K, and it took about, and it decompressed at about 15 megabytes per second, which is not super fast compared to modern Zip engines, but pretty fast still. So what's the point of these raw WASM demos? Well, mostly what I'm trying to do is do something fun, play around with what WASM can do, and do it all by hand. WASM is meant to be written using a programming language like C++ or Rust or Go or AssemblyScript or many others. But you can write it by hand, just like you can write assembly by hand. So what I tried to do is see, what can you write by hand? So how did I do it? Well, usually I actually don't use very much at all. I program in Vim. I write some Python scripts to generate data for myself. I use a tool that I wrote called WAT2WASM. This is part of the Wabbit toolkit. And then I use a browser, and that's it. So it's actually not too hard to get started. You don't have to do a lot of setup. So I'm going to show you exactly what I do. So the rules that I have for making a raw WASM demo is I try and use as little JavaScript as possible. You can use more, and that's okay, but I like to try and make it as much WASM as I can and use as little JS, because JS allows you to do a lot of things, right? One of the fun parts is if you're trying to make WASM really small, is to try and use as little WASM as possible. So that's the second rule, is try and make the WASM as small as possible. And then the third thing is always just try and have fun. You know, people don't expect that you can do fun things in WASM, because, I mean, I guess a lot of great demos are in WASM, but I don't think a lot of people expect you can do really fun things just writing it by hand. So that's kind of what I wanted to show. Here's some cool stuff you can do. I hope you thought those demos were cool. So what are we going to talk about today? Well, for this talk specifically, I made a new little demo. You've probably seen a game like this before. It's called a Match 3 game. There's many, many Match 3 games. I won't name them all, but you've probably seen some like this. So what you can see is that as I move my cursor around, we hover and we can show which cursor or which item I'm pointing at. If I grab an item, I can swap it with the one nearby. It clears it, moves everything else down, and resets. And you can see my score increased too. So I'll do it again. I'll do it again. Hopefully I'm not missing something that you're seeing. Okay, so you can get the basic idea. This is the sort of game that we're going to make today. I'm not going to show you all the steps because there's too many steps and this talk would take quite a bit longer, but I will show you a lot of the interesting steps. If you want to see more of the steps, I'll have the link at the end and you can look at the code yourself. I'll make sure that all the code there is very easy for you to read and follow. So let's get started. So how does our match 3 game work? What are the rules? Well, as you saw, there was an 8x8 grid of different emojis. So these were ones that my sister helped me pick out. They're the ones that she really liked the best. You could probably guess that the poo emoji was a very important inclusion for her. So we have 8 different emojis, and the rules are that whenever 3 adjacent identical emojis are in a row, horizontally or vertically, they're removed. And then when emojis are removed, then all the cells above fall down into their place. Now, how do you play the game? Well, what you do is you can pick any and you swap it with the one nearby, either horizontally or vertically. And if there's no swaps left, then the game is over. I didn't show you that before, but we'll actually show you some of the steps of that at the end of the talk. So let's dive into the code. I mean, this is a technical talk. Let's get messy. All right. So for the first step, I like to create, and in fact, usually what I do is I just copy some HTML and JavaScript and some CSS from the previous examples that I've done before. So here is some of the CSS that I find works really well for my demos. First, I make a flex box of the body. That means that it'll fill the entire space and then allow you to stretch the values, the elements out. I make sure that that flex box fills the entire screen. Then I create a canvas element inside, and I make sure that it maintains the aspect ratio, because one thing that looks really bad is when the aspect ratio is squashed or stretched. So we want to make sure that we keep that aspect ratio. And then I make sure that the pixels are nice and crisp. And then finally, we take that body and insert a canvas. And in this particular case, we only want 150 by 150 pixels because our grid is actually 8x8. Each one is 16 with a 1 pixel gap. So that gives us a nice small canvas to render into that we're going to be rendering by hand. So next step, we create some WebAssembly. So actually what you see here is not WebAssembly, this is JavaScript. But we'll get to the WebAssembly in a second. So the very first thing you need to do when you have a WASM file is you need to fetch it, which is what we do here, and then take the bytes out so that we can actually instantiate the module. So then the next thing we do is we take those module bytes and then we instantiate the module, and it creates a module and an instance. Probably some of the other talks will talk about the difference, but for now, the important thing is that the instance is what we actually care about. So our instance has some exported values. One of those exported values is a memory object. So we take that memory object and then we extract the array buffer from it. The array buffer represents the entire array of bits and bytes that we can access inside the memory buffer. And finally, we create a view over that memory buffer for the entire data that we're going to use for our canvas. So we use the width, which is 150, and the height, which is also 150. And then we multiply by 4 because each pixel is 4 bytes. And that gives us a view into the WASM memory, which we will then copy into the canvas. So you can see a little demo here that I made, just sort of showing you an example of how you can think about the memory being laid out inside the WASM module. So these slides should be up now. And you can take a look at them. And so if you want to understand better how this is all working, you can play around with them. They're all, a lot of the figures in this talk are interactable. So you can see up in the corner, we have the address here, which is 10,000. That's the address that we put our Canvas data at. And in the bottom corner here, can't quite get it. We have 25F88, and that's the end of the canvas data. So as you move around, you can see that the address is updating. Okay. So then what we do when we actually want to copy the memory from WebAssembly into the canvas is we have to create a canvas rendering context, then create an image data of the width and height that we want to render. And then every frame of that we're rendering, which is about 60 frames per second, depending on your window, we run the WASM function to update the data. And then we copy that data into the canvas using the image data and then using put image data. This is a little bit confusing. There's quite a few steps, but hopefully you've seen something like this before. And if not, you can, like I said, I mostly just copy and paste this from every project to the next. Okay, so let's start doing something with this canvas. The first thing, and probably the easiest thing to do, is to do a clear screen. It's a little simpler than a put pixel because we just have to do one loop. So this is how you define a function in WebAssembly. We say clear screen, and then we give it a parameter. In this case, it's the parameter is our color that we want to draw. So now we define a local variable. We call it I, and it's an int 32 variable. Now we can loop over all the pixels from 0 all the way up to 90,000, which is 150 times 150 times 4. So this is the instruction that actually writes into memory. It's called I32 store, and we can give it an offset. The offset we're giving it is where the start of the canvas is. So now what we can do is we can use that offset, add it to our index, and that'll be where we're writing the data. I'll have a little figure for this later. So every step we step by 4. Remember that the number of bytes per pixel is 4. So we're stepping by 4 and writing that color every single time. Okay, and so now we can call that function. We call the function by using the call instruction and then passing the name of the function and then the parameters. In this case, the parameter is the color red. You can see it's a little bit hard to understand, but FFOOOFF is written in alpha BGR format. So we have an alpha of 255 and a red of 255, which is FF. And this gives you a little example, again, another interactive figure of what actually is going on here. So you can see that as we step through all the I values, we're just going to go through and fill the entire screen with red. So now we've cleared the screen. Let's move on to drawing a pixel. So this is a little bit more interesting. Now we actually are taking multiple parameters. We take an X coordinate and a Y coordinate that we want to draw and a color. So the first thing we do is we take our Y coordinate and multiply it by 150 to figure out exactly how far down the screen we are. And then we add our X coordinate to figure out how far from the left we are. Then again, we multiply by 4, which is the size of the pixel. And then finally, we store our color at that address. So you can see on line 3 here, this would be how you'd write it in maybe a JavaScript-like language. And then finally, we can call our function just like we did before. This time we're passing 3 arguments to the function, the X coordinate, the Y coordinate, and the color. So our XY coordinate is 100, 100. And now here you can actually see the running WASM. This is in the slide directly, and we've got a red pixel. Hooray! We're almost done, right? Okay, let's keep going. We've got a lot more to do. So next, we want to be able to interact with our demo, right? And so we want to get input from the user. This is another place we have to use JavaScript. So what we're doing here is we're creating a view over the first 3 bytes of memory. And what we're going to put in there is the X coordinate of the mouse and the Y coordinate of the mouse, and then the buttons. In this case, the buttons is actually a bit mask of all the different buttons, but we don't really care. We just are going to say if any button is pressed, then that's a button for us. So we'll write those into the first 3 bytes, and then we'll hook up event listeners for each of our common mouse events: mouse move, mouse down, and mouse up. Okay. Now, what I like to do is make sure that I know what's going into memory inside our WASM module, because it can get pretty confusing because there aren't any variables like you'd see in a normal language. It's pretty low level. So it's important to make sure you're keeping track of where you're putting things. So what I do is I put a little memory map at the top and I say, okay, 0 is the X position, Y is at 1, and the mouse buttons are at 2. Now, here's a new instruction. Instead of doing a store, we can actually do a load. In this case, we're doing an 8-bit load from 0 to get the X, and from 1 to get the Y, and from 2 to get the buttons. And now we can use a different instruction called select. Select takes the last parameter here, the last argument, and it says if it's 1, then choose this value, the top value, and if it's 0, choose the other value. So it's kind of like an inline if instruction. And so this is either going to be red or blue. And so we can see a demo of that here. So I hope you can see the blue pixel here. And then when I click, it turns red. Okay, we're getting closer. All right, so how might you fill a rectangle in JavaScript? It might look something like this. In WebAssembly, it's going to be a little bit more complicated. You can see there's a lot more going on here, but it's the same basic structure. So what we have is our parameters here, x, y, width, height, and a color. Again, we create local variables just like we did in the JavaScript example. And then we have our outer loop. This is our loop that loops over the y coordinates from 0 to h. Then we have our inner loop, which loops over the x coordinates from 0 to w. And you can see here we actually have to reset the I value to 0, because after we loop through the first time, it'll be at the end, so we have to reset it. But we don't have to do it back here because all local variables start off at 0. And then finally, we do our put pixel. We already have put pixel, so we can reuse it. We take our x coordinate, which is the upper left coordinate where we want to draw the rectangle, and then we add in our offset, and then we put that color. Okay, so now you can see a little demo here, and we have a little rectangle that we can draw. And when we click, it turns red. All right, pretty good. Making progress. So now let's say we want to draw a sprite instead of drawing a rectangle. So what we'll do is instead of taking a color as our parameter, what we're going to do is take a source as our parameter. And this is the source of data that we want to read. The source is a pointer, and if you're used to writing in a language like C, you might expect to see something like I32 star or U8 star or something like that. But in WebAssembly, we do it a little bit differently. We say that pointers are basically just 32-bit addresses that are an offset into our memory. So that's why we use an I32 here. Okay, so now we want to calculate the pixel color that we're going to use. So what we do is we calculate how where the j coordinate is, multiplied by y. That actually gives us the vertical value. And then we add in our I, and we multiply by 4, and then we add in our source, and that gives us the location inside the sprite. I'll show you a little demo for that. And yeah, so actually here we have a load that's not an 8-bit load, it's a 32-bit load. The reason we're going to do that is because we want to load a color, which is 4 bytes or 32 bits. And then finally, we actually have to include our sprite data. You might think we would load a ping or load a GIF or something like that, but actually instead what I want to do here is embed the data directly into the WASM. Remember, we're trying to do as much in WASM as possible. So you can see that I'm just including the raw data here. It's a little hard to understand, but if you look really closely, you might be able to see the picture that we're loading here. So here's a little figure that shows exactly how that might work. So you can see our source image is over here on the side, and our destination image is over here. And as we go through our steps, we draw all the pixels. And you can see also that we can move the x coordinate to the side. Now, one thing you might notice is that if we overlap, it actually wraps around to the other side. This is because we're not actually doing any bounds checking. We're not doing any clipping on our sprite. That's pretty important, so we'll do that next. So the way we can do this is now inside our put pixel function, we'll check to see if our pixel is in bounds before we draw it. So the way we can do that is using the BRF instruction, which we've seen before. But now if we say BRF 0 at the top level, it's kind of like saying, if this is true, exit the function. And so what we want to check is, is the x coordinate greater than 150 or is the y coordinate greater than 150? And that allows us to branch out if the pixel is out of bounds. Another thing we want to do is make sure that we mask out transparent pixels. So what we do here is we load the pixel and we check to see if it's 0. And if it's non-zero, then we draw it. So what you can see here is that now we actually have a nice little sprite that we're drawing, and it doesn't overlap with it doesn't mask out the sprite below it. Okay, so like I said, I can't go through all the steps, but I do want to show you a little bit about what other steps we're doing here. So one thing we're doing is we're drawing with a palette. Well, actually, you can see this doesn't really do anything differently. What's different? Well, one of the things that's different is that now I'm actually using just 1 byte for a pixel of the sprite. That actually reduces the size quite a bit by 4x for each of the sprite data. So that is one way that we can save a lot of bytes, and I do that in a lot of the examples. All right, let's do something more fun. Let's take our sprite and scale it up to different sizes. So now what we're going to do is take our width and our height and change it to a source width and a source height. That's the source image, basically the sprite data that we're loading from. Then we add a destination width and a destination height, and that's the size that we want to draw it to. Now we create 2 local variables. This is the first time we have floating point variables. So these floating point variables are going to represent the scale factor in each dimension. And then we build up our scale factors using this formula. We take the width, the source width, and divide by the destination width, and the same for the height. And now it's actually a pretty small change. If we just take that scale factor and multiply it by our coordinate, then that gives us the new source coordinate to use when we want to read the pixel. So I have a little demo here again, and you can see that now when I scale out the destination width or scale out the destination height, you can see that the image scales as well. And if you look at the source here, you can see that as the steps go through, sometimes it actually uses the same source pixel for different rows. And that's what gives you this nice scaling factor. Okay. And if we look at the demo, now we can click and get a much bigger smiley face. Hello. Okay. So now we actually have to represent the grid. So one way you might do this if you're writing this in JavaScript is you use 1 byte per cell, each byte representing one of the 8 different emojis. And you could do that, and it would look something like this. I won't dwell on this too much, but you can see that each of these cells represents a different emoji. And if I switch to the value, you can see that like all the little purple faces are the number 2, right? And this would be our array of data. But instead, one thing we could do in WebAssembly that's a little bit easier to do than in JavaScript is we can use 1 bit per cell. And so that might look a little bit like this. Because we have a grid of 64 cells, we can actually use a 64-bit number to represent our grid. So again, this is a little bit tricky, but if you look at the blue highlights here and the blue highlights here, this shows you which bit is set for each element. So you can see we have the cowboy face set here, and we see the cowboy face bit here. If it's 0, that means that we're not displaying those faces. Okay, so how do we do that in WebAssembly? And why would we do it? Well, one reason we do it is that actually makes some of the algorithms later a little bit easier. So we'll see that in a little bit. Okay, so the first thing we're going to do to draw the grid is we're going to take our 64-bit number, and if it's 0, that means we're done. Otherwise, we're going to find the lowest index bit that's set, and we're going to draw an emoji at that index. And then we're going to clear that bit and then go to the next one. Okay, so this gives you a little example here. You can see we have the 1 bit set here, and if I go to the next step, we clear it, and then we draw a little poo emoji at that cell, and then the next, and then the next, and then the next. So you can see that when we're done, it's all set to 0, and that means that we've drawn the full grid. Okay. So this is some of the code for that. I won't step through it because I'm getting a little close on time. But you can follow through on this in your own time when you are looking at the slides. So the one thing I want to talk about here is another interesting instruction that we don't actually see in JavaScript, which is called CTZ, which is count trailing zeros. This will give you the index of the lowest bit that's set in um, the bit mask in the I64 value. So that's how we're determining which bit to do next. And then the way that we clear the lowest bit is actually using a nice little bit hack. If you take the number and you AND it with the number -1, that'll clear the lowest bit. Takes a little bit to understand why this works, but you can read some online documents about how this works. And this is another nice little trick that you can do to try and keep things small in WebAssembly. Okay, and so now what we have is this beautiful grid of emojis. Excellent. Okay. So let's talk a little bit how we do animation. So one thing you'll notice is that if you have a linear animation, it looks a little bit, I don't know, unnatural. If you set it to something cubic in or cubic out, it looks a lot smoother. So we want to do that here too. So what I added was a linear interpolation function. So this linearly interpolates from A value to the B value with a T value representing from 0 to 1, how close you are to A or how close you are to B. So again, I won't step through all the code here because of time. Okay, so now we also want to take that linear interpolation and then use a cubic interpolation so that we get that nice smoother curve. So this is the formula for that. Nothing too new here, but it is a way to represent this formula here. You can see well, you can see the formula here, and this is how you would write it in WebAssembly. And so now you can use that cubic function to interpolate between two values, for example, 10 and 30. And this will pick the cubic interpolation halfway between, and that'll make a much nice smoother curve. Okay, and so this is the code that we're going to use here so that each cell gets its own animation values. So I have a certain structure, which is the X, Y, and W, width and height offsets. Normally we just draw them in a grid, but now we can have an offset so they can offset in any direction. We have a time value, just like we said before. We have a starting value for each of the cell elements, and we have an ending value. And then what we do is we actually use the formula we saw before, calculating that interpolation, and then we store that value into the current offset, and that's the offset we'll use when we're drawing the cells. So what you can see now is we actually have little zooming when we mouse over things, and that's using the animation that we set up just now. Okay, so again, trying to fast forward through some of the steps because we only have so much time. We can add things like dragging the emoji. This is the basic step where you grab an emoji and then you can drag it, and when you release, it animates back to where it was. The next step we might do is grabbing an emoji and then only allowing you to move to one of the 4 adjacent cells. Okay, but still we don't have swapping yet. Okay, so the next step we will add is swapping with the one nearby. And again, this is just using the same animation stuff that we had before. We can see that the nearby cells are swapping with us. But when we release, it just swaps back. And then finally, we have what feels almost like a real game, is that when we release, it'll swap with the one nearby, and it'll stay that way. Okay, but you can see it's actually not removing them yet. So let's talk about how we're going to check for matches. Remember how I said that 1 bit per cell makes some algorithm smaller? Well, this is a case for that. This is a pretty complicated demo, but you can explore this a little bit on your own time. What we're seeing here is actually a pattern. See these bits here? These bits represent the pattern that we're checking for. And this is the grid that we want to find. This list right here is whether that pattern is valid. So as you can see, I stepped through, these patterns are all valid, but right here, we're actually wrapping around to the next cell. This is not a valid pattern anymore. So we set a 0 bit here. So as long as we wrap through and we see that all of them are set, then we see all these bits are set here and the bit is valid. Therefore, this is a valid match. We can do that for horizontal and vertical steps. So hopefully you can play around with this and see how that makes sense. So this explains a little bit about how that function works, which is what I just explained to you. And here's some of the code for that. Again, I won't dive too far into the details here because we don't have time, but this gives you an example of how you can step through and find that. And finally, we take each of these patterns and we just lay them out in the bits directly in memory. And so now we have our horizontal pattern and our vertical pattern, and then our valid bits stored as just very small values. And we can use those same functions for each one. And what that gives us is whether or not we actually made a match. So now you can see that when I drag, I get a nice little match here. Okay, hitting the home stretch here. So fast forwarding through some of the new steps. One thing you can notice is that if I swap and there isn't a match, oh, actually that was a match. Okay, if there isn't a match, now it moves back to where it should be. I'm going to skip this one because I don't really have time for it, but very interesting, different new algorithm to show you how we actually fill in the slots, and a little demo here too that you can play with. Basically what's happening is we look at a cell and then we look at all the cells above and we find which one is the one that's most close above that is actually filled in. We use that to move down in the next step. And you can see here that the code to do it is actually not that much code. We do a few steps here that use bit masks, and then we use our good friend CTZ again, and then we can check to see if that cell is above, and if so, then we'll swap it down. And you can see once we do that, now we actually have elements falling. Okay. Again, to make it feel more like a game, we can randomize the cells at start. Now it's starting to feel kind of like a real thing, isn't it? Just like what I showed you at the beginning. Okay. And now we can check matches after dropping. You saw just there, actually, that as the matches fall down, we can start to get combos. And then we can animate the match removal. So now you can see we have a little zoom out effect that happens when we get a match, which is pretty cool. I think it makes it feel a lot more alive. Okay, one last thing, go through it really quickly, but when we're checking for a game over, we can use the exact same matching technique that we use that we're checking for matches. And one of the cool things about that is that we have all these different patterns, but the code actually stays the same. So if we check for this pattern, now we're checking to see if there's anything that can swap this way. Let's see if I can find a different one. There's one. So what you can see now is that if this is showing a place where I could do a swap and get a match. All we're doing is we're using a different pattern, but now if we check all these different patterns, we can check for game over. If we don't find any patterns, that means that we don't have any cells left to swap. So yeah, again, feel free to play around with this. Just showing you some of the patterns here. This is one of the really cool things about keeping it small. We just add new data in our horizontal patterns and our horizontal valid masks, and that shows us that we can expand to a lot more cases with the same amount of code. Okay, so we're done, right? Well, there's a few more things here that I've done. We need to implement scoring for the game, which I've done here, but I haven't shown you. We probably want a title screen and a game over screen. I haven't done that yet. Maybe we want a combo multiplier. And actually, we want to optimize the size too. Right now, this is my biggest demo yet at 4,000 bytes. So I definitely need to slim this down. But that's pretty much it. This is how raw WASM feels. It's a lot of solving fun little problems. Again, if you want to see these slides, please go to this link. If you want to know more about raw WASM, please go to the second link here. If you want to know more about Wabbit, the WebAssembly Binary Toolkit, this link is probably one that's going to help you. That's how we convert our WASM file from text to binary. And if you want to follow me on Twitter, yeah, my name is Benjamin. And you can see right here, I have a little mini version of the game running. So thank you so much. And I hope you enjoyed.